How do transfer functions troubleshoot physical systems? Imagine trying to fix a machine without knowing how it actually behaves. That's where transfer functions come into play. They act like a map showing how a system responds to different signals. Transfer functions are mathematical tools that help engineers understand how a system reacts to inputs. They show the relationship between what you put into the system and what comes out. This makes it easier to spot problems before they turn into failures. A transfer function is written as a ratio. It compares the Laplace transform of the output to the Laplace transform of the input. This ratio tells us how the system behaves across different frequencies. By analyzing this, engineers can see if the system is stable or if it might cause issues. One key way transfer functions help troubleshoot is by looking at poles and zeros. Poles are points that tell us about system stability. If poles are in the left half of the complex plane, the system is stable. If they are in the right half, the system can become unstable. Poles on the imaginary axis mean the system is marginally stable. Spotting these helps engineers decide if adjustments are needed. Transfer functions also reveal how a system handles different frequencies. For example, some systems filter out high frequencies while passing low ones. By analyzing the transfer function, engineers can see if the system is passing signals properly or if it's distorting them. If a circuit meant to pass audio signals is attenuating them, the transfer function shows where the problem lies. Another way transfer functions aid troubleshooting is by predicting transient responses. They tell us how quickly a system reacts, how much it overshoots, and how long it takes to settle. If a system responds too slowly or oscillates too much, the transfer function points to the root cause. Engineers can then tweak components to improve performance. In electrical circuits, transfer functions are derived using impedance and voltage divider principles. For simple circuits like resistors and capacitors, the transfer function shows how signals are attenuated based on the circuit's parameters. If the actual behavior doesn't match the predicted transfer function, it indicates a component failure or parameter change. For more complex circuits, like those with resistors, inductors, and capacitors, the transfer function reveals resonant frequencies and damping effects. Deviations from expected behavior can signal issues like component damage or parasitic effects. Transfer functions also help in modeling systems without building physical prototypes. Engineers can predict how a system will respond to different inputs. When the real system behaves differently, the transfer function comparison helps identify what went wrong. It could be component wear, environmental factors, or design flaws. In control systems, transfer functions are essential for designing controllers that keep systems stable. They help engineers see where the poles are and how to move them to improve stability. This way, they can prevent oscillations and ensure the system performs as intended. Overall, transfer functions act like a diagnostic tool that turns complex system behavior into simple mathematical relationships. They help engineers find problems, understand their causes, and fix systems efficiently.